Good evening, everyone. Welcome to BCS Coventry meeting for November 2023. My name is Dr. Diana Basin Kantar. I am the chair for BCS Coventry. Our topic for this meeting is real quantifier elimination, recent algorithmic progress and applications. And our speaker is Dr. Matthew England. Matthew is the co-director of the Coventry University Research Center for Computational Science and Mathematical Modeling, and his main research interest is in algorithms for symbolic algebra and symbolic logic, in particular for solving problems with real polynomial systems. And he currently leads the EPL-SRC-funded QE project, which is a project on pushing back the doubly exponential wall of cylindrical algebraic decomposition. And it does lead a group of related postdoctoral and PhD students. It's worked on many projects, including projects on the use of machine learning for algorithm optimization and the integration of computer algebra systems and satisfiability modulo theory solvers. Welcome, Matthew.
Thank you, Diana Bassi. Let me try and share my slides again. Can you see them okay?
Yes.
Okay. All right. Well, thank you very much for your invitation and kind introduction. So indeed, I will talk on that topic. And I should acknowledge my funder, the EPSRC. So my talk is in 3 parts. So the first part, I will just simply try and define what is quantifier elimination or real quantifier elimination. So this is essentially background material. So if you're not familiar with this term, that's fine. Hopefully I will define it well for you. Then in the second part of the talk, I will talk about some real applications that we can use this technology to tackle. So here I try to convince you that it's an interesting thing that can have some positive effect on the world. And then in the third part of the talk, I can mention some of the ways we've improved the algorithms in this area. And here I will try not to get too technical, but stick to some of the main messages, which is about integration of different areas of computer science and how that was profitable for us. And perhaps those messages resonate beyond quantifier elimination to other areas of computer science as well. So I should just say that if anyone wants to ask a question as we go through, I'm very happy to take them. I'll probably pause after each section in case anyone has any. So I'm going to touch on lots of different topics. So the work is joint with many people over the years, and I tried to list them all here. I do hope I didn't forget anyone. I'll also say that these slides are on my website should anyone want to download them for the references and so on. Okay, so let me start by trying to define the quantifier elimination problem. So the problem is that you are given a logical formula that is quantified. That is to say, it has the quantifiers either there exists, which is the backwards capital E, or for all, which is the upside down capital A in it. So I guess I'm talking here about first order logic, like we all would have learnt at the start of our computer science degrees. I will assume that the formula is in pre-nix normal form, which means the quantifiers come at the start of the formula. But if that's not the case, it's easy and possible to convert the formula into that form. And then for me, what makes it real quantifier elimination, as opposed to any other kind, is that the logical atoms in the formula are going to be polynomial constraints, so the world of mathematics or algebra. So given such an object, a formula, the quantifier elimination problem is to produce another formula that does not involve quantifiers, one that is quantifier free, but that means the same thing, or at least means the same thing over the real numbers when those algebraic variables take any real number value. So that's a bit of a mouthful to say, but the examples will hopefully make it clear. So let's look at some examples of quantifier elimination. So the first example, it reads, there exists an x such that x squared plus 3x plus 1 is greater than 0. And the equivalent quantifier free statement is true, because that statement is unambiguously true. For example, if x equals 0, then the statement becomes 1 greater than 0, which is always true. So there's no doubt here. An equivalent statement is just the word true. What about the second example? Here it's the same polynomial constraint, but the quantifier is different. It now says for all x. And this statement is false. So for example, when x equals -1, the formula becomes -1 greater than 0, which is a false statement. So this formula is not true for all x. It's true for some x, as we've just seen, but it's not true for all x. So here, the quantifier elimination would produce false. In this third example is an example where something is true for all x. So x squared plus 1 is always greater than 0 because the square of any real number is positive, and adding 1 also keeps it positive, so that is true. So these examples are very simple because they all boil down to true or false. So let's look at an example where that's not the case. So here, for all x, x squared plus bx plus 1 is less than or equal to 0. So what is the answer here? Well, as you may be able to see, it's going to depend on what b is. The answer is going to depend on b. So let's study this. I realize now a typo, my first typo in the slides. I meant to study the problem greater than 0. So I do apologize for that typo on my slide. I'm trying to study the problem greater than 0 because then we see that the two problems I explained to you are subcases of it. We saw that this is the case b equals 0, where the answer was true, and this was the case b equals 3, where the answer was false. So how are we meant to answer the question when we don't know what b is? So one kind of experimental approach we might do is to plot the algebraic relationship, which is what I've done here in the red line in the case b equals -4. And we see that when b equals -4, for some values of x, the algebraic polynomial is negative, and for some values it's positive. And here I plotted it with b equals -3, that's the same. And here b equals -2. And when b becomes -2, the curve rises above the x-axis. So now the constraint is always positive, except just at that one point where it touches. And indeed, if I go up to -1, it's now fully always positive. And I can keep playing this game. And what's interesting is when you start making b positive again, the curve starts to go down and then eventually cuts down there into the negative part again. So if one puts together these experiments, one comes to the conclusion that that formula is true when b is greater than -2, but less than +2. And so what I would say here is that an equivalent formula to the input that doesn't involve quantifiers is the formula b greater than -2 and b less than 2. So this is an example of a more interesting case of quantifier elimination, where the answer is not just true or false. The answer is a statement that is a logical statement in the variables that are not quantified. And so that's really the way that you should think about quantified variables. So quantified variables are somehow not actually there in the real world. They're more of an expressive construct to allow you to describe what might be quite complicated conditions on the unquantified variables. So the actual problem always boils down to a statement in the free or unquantified variables, in this case b. So this is not obvious, and indeed it's not true in all contexts. So it's true in my context of real quantifier elimination, where the logical formulae are formed from real numbered algebraic constraints, but in other logics, in other for other types of logical atoms, quantifier elimination has been proven to be impossible. So it's quite remarkable that it is possible in the case of the real numbers. And that goes all the way back to 1945, the work of logician Alfred Tarski, who proved that such a process is possible, even before he had a computer to implement it. So I hope I've adequately explained what real quantifier elimination is. Although if anyone had a question at this point, I guess it's a good point to ask it. And what the rest of the talk is about is really how can we do this? So what's wrong with making the pictures like I did here? Well, drawing those pictures and observing what happens is fine for getting an idea, but it's essentially what we call a numeric computation. So I'm trying some values, seeing what happens, and then interpolating, in that case just in my head, to get a solution. The alternative is to use some kind of symbolic computation. So symbolic computation is the field of computer science and mathematics. It's interdisciplinary, that studies algorithms and data structures for manipulating exact mathematical expressions and objects. So traditionally, this has been implemented in what are called computer algebra systems, which are big pieces of software designed for mathematicians or maybe engineers to make use of. Maybe you've heard of Maple or Mathematica or Sage. Something your students may well have heard of is Wolfram Alpha, which is actually a website that hooks into an underlying computer algebra system. So what are the advantages of a symbolic computation approach? Well, number one, they can be more reliable than numerical computation, especially in the case where the problem is what's called ill-conditioned, where it somehow is not well suited to the numerical algorithms. It can provide guarantees if you're in a safety critical context. If you're doing something where you really want to you really need that guarantee that the solution is 100% correct all the time. And the third one, which is I guess the most interesting for me, is that it can provide fundamental insight into the system. So the structure of that quantifier free formula that you get out can often tell you something about what the system is doing that is hidden in the quantified version. So it's kind of can be thought of as a form of mathematical simplification that allows you to better understand the mathematical object than the original form. So those are the advantages. The disadvantages is it's very expensive, as we'll see. But there's still hope to make it better. Okay, so that's quantifier elimination. And my next section, I'll describe the best known tool for performing real quantifier elimination, and that is CAD, which in this talk stands for Cylindrical Algebraic Decomposition. So once again, I'm going to give the definition, which is quite heavy and mathematical, but then I'll give an example, which I hope will make it all really clear and easy. So first, let me give the definition. So what is a cylindrical algebraic decomposition? Well, I define each of those words in turn. So first of all, it's a decomposition of n-dimensional real space. So what does that mean? It means I'm chopping up this space that's of interest to me into smaller chunks. I'm going to call those chunks cells. And each cell is a connected chunk of the space. And if I take all of the cells and put them together, the union there, I get the whole space. But none of the cells overlap. They're all different to each other. Then I have two other words here. So algebraic is actually a bit of a misnomer. It should be semi-algebraic. Semi-algebraic means that the cell can be described by a finite sequence of polynomial constraints. Constraints meaning either equations or inequalities. If it was just equations, it would be truly algebraic. But because I also need inequalities, it's semi-algebraic. So it should really be cylindrical semi-algebraic decomposition, but the acronym CSAD never took off and doesn't really roll off the tongue. The third word is what hides all the structure, and that is the word cylindrical. So the definition here is that the projection of any two cells, that is to say, if I take these cells in n-dimensional space and I squash them down into a lower dimensional space, then those projections are either exactly the same or they're completely separate. Or another way of thinking about that is that the cells in n-dimensional space are all stacked on top of each other in cylinders, like stacks of plates in your cupboard, over cells in the n-1 dimensional space. And this is both a desirable property, as we'll see in the coming slides, but it's also a facet of the computational algorithm that produces these. We work iteratively through the dimensions And so we end up with these stacks of space, stacks of chunks. Okay. I will show an example in just a sec. Before I do, I have one more word that I need to define. So these CADs at the moment, they're just an idea, but of course in practice they're produced for a reason. So the reason could, for example, be because one wants to perform quantifier elimination, and I'll talk about how they can be used to do that in a moment. But they can be used for lots of reasons to do with studying polynomials. And so what they're usually produced with is that you have a set of polynomials and you produce the CAD relative to that set of polynomials such that the CAD is what's called sign invariant for the polynomials, which means that each polynomial is either positive, negative, or zero throughout a given cell of the decomposition. I do have a side note here that in practice that's a little bit trivial, and what we really want is not polynomials but logical formulae. That's what we have in our quantifier elimination problem, for example. And what we really need is not sign invariance but truth invariance for the formulae. And there's lots of ways one can adapt to CAD to achieve this, but I'm not going to go through that so much today, those technicalities. What I want to get over is the big picture, which is that we're trying to study a system described by polynomials, and we're trying to study it over infinite real dimensional space. And what the CAD allows us to do is to take that infinite real space and chop it up into a finite number of chunks, such that on each chunk or cell, the behavior of the system is the same. And so the infinite becomes finite, and I only need to look at a finite number of sample points. And if I look numerically what happens at those finite number of sample points, I'm guaranteed to know everything about the whole infinite space, which is quite a powerful idea. Okay, so now the picture to try and explain this for those who couldn't quite follow those technical definitions. So here we have a circle. The blue circle here is defined by the polynomial constraint y squared plus x squared equals 1, or y squared plus x squared minus 1 equals 0. And if I was to build a CAD sign invariant for that polynomial, I will end up with the 13 red cells that are hopefully animating on your screen right now. So what are the key points to take away here? Well, the first one is that we have a decomposition. So these 13 cells together make up the whole of the two-dimensional real space that is the plane, but they don't overlap. Secondly, each cell is algebraic because I can define it relative to some polynomials, not just the polynomial that defines the blue circle. I also need the polynomials that define the dotted black lines on either side in order to define those cells. So that's an important point. It's not just the input polynomials that are required to define the cells, but possibly others as well. And what about this cylindrical property? Well, what hopefully you can see here is that each of these red cells lies within one of 5 cylinders. So the middle chunk here has 1, 2, 3, 4, 5 cells. But if I was to squash it down onto the x-axis, it would just be that one portion of the x-axis between -1 and 1. Similarly, if we look at this cylinder here, it's a smaller cylinder. It's that line which is split up into 2 half lines and the point. So hopefully that illustrates those 3 definitions. Okay, so that is what a CAD is. How does one produce one algorithmically? Well, that's a bit complicated, but I'll explain the basic idea. So the basic idea takes the input polynomials and it produces from them a larger set of polynomials. It contains those, but there's other polynomials as well. And those other polynomials are produced according to mathematical processes that define interesting features of the geometry of the curves. And then some of those polynomials are in just one variable, some will be in 2 variables, some will be in 3. And so what we then do is work iteratively, starting with the univariate polynomials and producing from them a decomposition of the real line. And then for each cell in the decomposition of the line, I substitute a sample point, a single point in that cell, and I substitute that into the polynomials that have two variables, and that turns them into one variable polynomials, which I can then easily find the zeros of, and I use that to infer what would happen over the whole of the original cell. And why am I able to do this? Well, I essentially have the nice picture that you see on the left of the screen here, where we have polynomials defining hypersurfaces, but they're kind of nice pancakey hypersurfaces. I don't have folded pancakes like on the right, or pancakes that intersect each other. And so no matter which cell in that no matter which point in that bottom circle I choose to work at numerically, I basically get the same behavior in the cylinder above, which is to say there's 3 pancakes, one on top of each other. Now, that wouldn't be the case on the right-hand side, where if I pick a point on the left, I end up with 1, 2, 3, 4 things, whereas if I pick a point in the middle, it could be less. If I pick a point on the right, it's just 2. So what happens is that those polynomials that we compute during the projection are basically chosen to identify situations such as the intersection of the pancakes, such as the turning over of the pancakes, that guarantee mathematically to identify those. And so what I ensure is that should something like that happen, because it's identified in the lower dimensional space, I would never have that as a stack that I'm building above. There would always be 2 separate cells in the lower dimensional space, and so the situation on the right couldn't happen. Now, I appreciate that's a little bit technical, and I've only given a hand-wavy idea there. You don't need to dwell on it, but I just wanted to give some kind of idea of how this works. And it relies on mathematical theorems guaranteeing that what we identify in projection produces these guarantees. Now I'll get back to hopefully something everyone's comfortable with, which is the idea of how we can use this for quantifier elimination. So I'm going to study an example, the same one, well, not quite the same one we saw earlier, and I'll explain why in a moment. I'm going to study the example x squared plus bx plus 1 is less than or equal to 0. Earlier we were studying greater than 0, and earlier we had for all. Here I'm looking at there exists, and I'll explain why I have a different example in a moment, but let's just first look at this example. So the blue curve that I've graphed is the polynomial x squared plus bx plus 1. So how would I perform this quantifier elimination? Well, I can start by building a sign invariant CAD for the polynomial x squared plus bx plus 1, and that would produce the decomposition that you see in the picture. I should say here the different colors are just to show the different cells. They don't infer any meaning other than that's one cell and that's another cell. The black circles, in case you're wondering what they are, the black circles are my choices of numeric sample point for when I study those cells. So that black circle where my mouse is hovering in the yellow region is a representative of the whole yellow region. So I build one of these CADs as I just described, and then what do I do with it? Well, then I take each of the sample points, each of the black circles, and I look at them numerically one by one, and for each one I answer the question, does there exist an x such that x squared plus bx plus 1 is less than or equal to 0, but at each sample point I know what b is and I know what x is, so that just becomes, is this number bigger or smaller than this other number, which of course I can answer very easily. And so I can tag each of those sample points either green or red, depending on whether it's true or false. And the power of CAD is that if it's true or false at the sample point, I infer the same behavior for the whole of the cell that the sample point represented. So I look only at that one sample point here, but I get to color the whole cell in green, and at the 0 it was false, and I get to color all of that great big cylinder false. And so now I know on which cells the quantified formula is true and on which cells it is false, or at least, sorry, the algebraic constraint. So I'm answering an existential question. So I know on which cells this algebraic constraint is true and where it's false, And I just need to find the cells where it's true, because that's what it says. Does there exist an X where it's true? So I simply project the true cells, that's the green ones, onto the B axis, and that will tell me for what values of B there did exist an X such that the statement was true. And we see that it's the cases when B is -2 or smaller, and the cases where B is 2 or greater. So hopefully that gives an idea of how this CAD process can answer a real quantifier elimination problem. So this process was introduced by George Collins in the 1970s as the first actual tractable algorithm that was implemented to answer these problems. So the original work of Tarski was a theoretical work that was never actually implemented. This was the first implemented algorithm to study the problem. This wasn't quite the problem I showed you earlier. So now let's go back to the problem I showed you earlier. So that's just an example. In general, to perform real quantifier elimination, you need to eliminate existential quantifiers by projecting true cells, as I did in the previous example. But what about universal quantifiers? Well, with universal quantifiers, we need to remember this relation that you probably learned in your first year logic course of a computer science degree. For all Px, P of x is the same as the negation of there exists an x of the negation of P of x. So if I study instead the negation of the algebraic formula, I can then use existential QE, and then I simply negate my result, and that's the same as doing universal QE. So now I look at the actual example that we studied numerically at the start. For all x, x squared plus bx plus 1 is greater than 0. The negation of that constraint is x squared plus bx plus 1 is less than or equal to 0. And I then study that existentially, which was the example from the previous slide. I know the answer is b has to be less than or equal to -2 or greater than 2. So I simply negate that answer, and I end up that b has to be between -2 and +2, which is what we discovered numerically at the start. However, unlike the result at the start, there's no room for any numerical error here. Remember, the result at the start I just got by drawing some pictures and guessing. Here I have a sequence of logic and algebraic statements that allow me to make this conclusion with 100% guarantee. It's a guaranteeable fact, assuming my code doesn't have bugs. Okay, so that is the idea. So I said earlier that this cylindricity property was useful, and maybe I just want to reflect slightly on why that is. So once again, decompositions are useful because it allows us to understand infinite space with a finite number of samples, and the algebraic cells is useful because we can use that to extract the solution formula to build our quantifier-free formula from. But why is cylindricity useful? Well, cylindricity is useful because when you have cylindricity or cylindrical cells, then projecting the cells, you know, the bit where I squash things down onto the b-axis, that's a graphical idea. But if the cells are themselves cylindrical, that means that their boundary in that lower axis is explicitly defined as part of their construction. So when you have cylindrical cells, projecting is trivial, and so that allows them to be used for existential QE easily. And then the other thing that we needed with our quantifier elimination process was the ability to negate the answer, to look at the opposite of a cell. And that's also something that's really easy to do when the cell is cylindrical. So this cylindrical structure is kind of exactly useful for performing algebraically what I showed you there graphically in the quantifier elimination process. I guess algorithmically, you can also think of it as kind of a tree structure that iterates out by variables. So first we decompose x, and then we, on each cell there, we decompose y. Okay, so I hopefully have, if I've done my job, explained how CAD can be used to do quantifier elimination. So what's the problem? Well, the problem is it's really, really expensive. So by the end of the projection phase, this studying, creating new polynomials that capture the geometric properties, you actually end up with doubly exponentially many polynomials, and each of those polynomials has doubly exponential degree, where the variable of the complexity is the number of variables. And so the number of real roots, and thus the number of cells and the time to compute them, all growing doubly exponentially. So this is horrible. So in practice, it means that kind of with small number of variables, 4, 5, it might be fine, but then you hit what I like to call the doubly exponential wall. And unless you use something smarter, then you can't really go beyond that. And so to illustrate that doubly exponential wall, I'd love to show you this picture here. This is a photograph, or 2 photographs, that were obtained by my PhD student, Teresa, when he went home on his holiday to his hometown in Spain and worked with his friend who is a farmer and grew some piles of grain to show both exponential growth and doubly exponential growth. So exponential growth piles are shown there on the left-hand side, the piles doubling in size each time. And that's pretty bad. That's some pretty bad growth. As we know from COVID, exponential growth can really get out of hand given a few weeks. But what we see here on the right is doubly exponential growth. Thank God COVID didn't have doubly exponential growth, because it would have got out of hand in just a few days in that case. So here, 2, 4, 16, 256, 65,000, and the one after 65,000 is in the billions, 4.5 billion. So that's really showing you what I like to call the doubly exponential wall, which is everything looks kind of manageable if you have a decent computer, and then you go one step further and suddenly it's out of the realm of a supercomputer. If you have a doubly exponential algorithm, there will be a wall. It's just a matter of where it hits you, and you don't have to go very far until you hit it. Okay, so that's obviously a problem. But that being said, if the problem you want to study is before the doubly exponential wall, then you can definitely study it. And this is not a theoretical thing. These algorithms are implemented in a great variety of mathematical systems. If your university has Maple or Mathematica, you can access it through those. If they don't, then you can download something for free called CAD, which is a free quantifier elimination via CAD tool. And if you don't even want to download it, you can even run this in your browser. So you can actually run this stuff in your mobile phone browser via this website here. So, you know, this stuff exists, and as long as you're studying a small problem, it works very nicely, and it can do the job for you. There's some other implementations for free as well, but they're a little bit more restricted. There are alternatives, but in the interest of time, I will skip discussing them in detail and just say that none of them are really better than CAD. And I'm now going to talk about some of my work. So everything up until now is essentially background, and I have work on applications and I have work on algorithmic ideas. And if people really want to hear one or the other, they're very welcome to request. But if no one says anything, I'll probably try and start with the applications. So I'll look first of all at applications in biology. In the world of chemical reaction network theory, we look at systems of the life sciences where you have reactants or maybe species, and they combine together to change behavior. So this could be predators eating prey, or it could be chemicals bonding and forming other chemicals, for example. So reaction network theory is a very nice mathematical modeling tool that can describe a very wide range of life sciences applications. So what you can do if you have one of these reaction networks is you can extract from them a dynamical system, that is to say a set of differential equations that describe how this system would lead to changes in the quantities of the variables over time. So for example, here that system leads to this that reaction network leads to this dynamical system. If we look, for example, at the change in x1, well, we can see that if you have 2 x1s and an x2, you end up with 3 x1s. So here the growth is 3 minus 2 is 1. The rate of the reaction is an unknown, k1, but it's proportional to the the quantities of x1 and x2, where you need to have twice as much x1, so the proportionality is double upon the x1. Okay, so I will skip a few of those mathematical details in the interest of time, and move on to what the actual problem is that I want to study. So when you have these dynamical systems, what a life sciences practitioner is really interested in is often not the system itself, but where it ends up. So with a dynamical system, it usually fluctuates over time, and then hopefully, not always, will end up in a steady state where the system is kind of balanced with itself. So the predators and preys are eating each other at a rate where they then have a constant population, or the chemicals have finished reacting and end up in a steady state. And that simply happens when the derivatives equal 0. And so what we move then from is the world of dynamical systems to the world of algebraic systems, which is the world that I inhabit. And what life sciences practitioners are often interested in is situations where those dynamical systems exhibit multiple steady states. That is to say, sometimes there are multiple places that you can end up. This is where the most interesting biological behavior happens, and where we want to study what we can do to end up in one rather than the other state. And so a key problem that we try to answer is where that can happen, where we can get this multi-stationarity. This is instrumental to cellular memory, things like cell divisions, and I guess in the long run, cancer can be answered. Well, not answered, but can be to cancer happen. Cancer happens only if you're able to have this multi-stationarity. So what we're interested in here from an algebraic point of view is for what values of the controllable systems in an experiment, that is to say the parameters, could this occur. So I've labeled, in all my examples, I label with X's for dynamic variables like quantities of a chemical, and K's are there to represent numbers that I don't know, but they're not varying over time. They're kind of fixed numbers in time, and often they're in the control of the person running the experiment. So not always, but often. And so being able to understand for what values of those numbers something can happen is an important ability. So we can study this numerically, and indeed that's what most life sciences practitioners do when they try to answer these questions. They pull out numerical solvers like MATLAB and so on, and they get answers, and that's fine, and it works for the most part, but it's not perfect. And this is, I guess, what this picture is seeking to illustrate here, is studying one particular system, and the correct answer at the sample points is blue or yellow. Blue is where there are multi-stationarity can occur. Yellow is where it can't. And that's the correct answer based on a fully mathematical symbolic analysis. And a leading numerical solver produced something that's almost the same, but the green and red points were errors. So the green points is where they said it was no multi-stationarity possible, but actually it was, and the red where they said it was when it actually wasn't. So there's some errors there, and you could probably look at it and guess which ones are errors, but it's not satisfactory, and especially on that boundary, you're not really 100% sure what's an error and what's not. So this is something that if we do this using a symbolic tool like CAD, we can avoid. However, that's about avoiding incorrect results. But what about the fundamental insight? This is what I consider more interesting. So what I'm showing you here is pictures produced by the work of my postdoctoral researcher, Amir Hussain Sadeghi-Manesh, who used the technology that we developed in our project to study a particular biological problem. It was in population dynamics, and he was seeking to explore a hypothesis that had been made by the biologist about the behavior of that system. And essentially the hypothesis was that if we increase the parameter a, you could only have fewer steady states. You couldn't have more. And if we look at this big picture on the left, that does seem to be the case. If you take any one value of b and you move across from the left to the right, increasing the value of a, indeed, the number of steady states decreases, 27, 21, 15, 9, 3. So it looks like that's true. However, if we zoom in on the region, this kind of spiky red region in the orange zone there, we see it's not true. That for b is 0.4014, for example, we can move across and we'll start with 15, then we'll drop to 9, then we'll go back to 15 again, then we'll go back to 9. So the point is that if one's just numerically sampling, the chances of uncovering this strange region are very rare. But if one has the symbolic solution, it's trivial to discover this. And so the symbolic solution was actually used to disprove a hypothesis being made in the life sciences, kind of forced the population dynamics researchers to revisit their assumptions about what this parameter a actually means. So kind of a meaningful theoretical contribution to the life sciences there. Okay, I'm, in the interest of time, going to skip some of the technical details here, just working for a really big problem. The key idea, which I'll just mention, is that one can't simply apply CAD alone here because I've got 14 symbolic indeterminates. Remember that doubly exponential wall that's out there. So 4 or 5 is okay, 6 is definitely not. So we can't just stick this into CAD. And what we found was that we could pre-process it using other mathematical and computer science tools, and essentially boil it down to a 4-variable problem, albeit a more ugly 4-variable problem, but one nevertheless that we could study with CAD. And we had a few different approaches for doing that, but the point I'm trying to make here is one has to be a little bit sensible and combine ideas from other domains rather than simply going straight to the doubly exponential algorithm. If you're interested in those details, I can refer you to the references. Okay, so that's just a taster of how we've been able to have impact with these ideas in the life sciences. I'd now like to move on to a completely different area of application, which is economics. So I'd like to pick these two applications because they're so different, but they're both kind of a surrender to the same technology. So within economics, the way economics researchers, or certainly the theoretical ones, tend to work is that they make assumptions about the world that they're studying, and then they try to prove mathematically or empirically that certain results happen if you have those assumptions, or hypotheses, if you like. So economists kind of conjecture these ideas about the world, and then they try to prove it or to observe it. But there's no guarantee that what they conjecture about the world is true. Sometimes there are examples in the literature where they've put together a bunch of assumptions that are themselves contradictory. So they've assumed two things that can't actually happen simultaneously. That's a terrible starting point. Sometimes they've hypothesized something that's just not true, but maybe they could throw in some additional assumptions to make it true. There's just some additional things they need to assume about the world. Or maybe they've actually gone and proved something to be true, and maybe they're assuming more than they have to. Maybe they can remove some of those simplifying assumptions so that their results have wider reach and appeal. So all of these kind of approaches to economics can be dealt with by real quantifier elimination if the assumptions and hypotheses they're reasoning with are describable by polynomial constraints, which they commonly are, not always, but commonly. So we have a package in Mathematica called Theory Guru. Theory Guru is essentially just a wrapper around Mathematica's normal real quantifier elimination package that tries to present it in a way that economists are familiar with. So economists present their assumptions and their hypotheses, and we then make two real quantifier elimination calls, and that allows us to identify which of those possible cases they're in. Either they prove something true, or maybe they've got some contradictory assumptions, or that what they've proven, it's kind of mixture. Some of the hypotheses are true, but some aren't, but maybe we can identify which ones for them, or maybe it's hopeless and we can't do much at all. So let's take a look at an economics example. This is what's considered a very classic early work in economics by Marshall in 1895, who talked about the relationship between supply and demand, and he considered what happens if the resources used to produce a product get cheaper, so the supply costs go down. And a classic result in economics of Marshall is that if this happens, then what you should see is an increase in the quantity of goods being produced and a decrease of their price. This is somehow what should happen in the world if the cost of the supply goes down. So how do you kind of formulate that mathematically? Well, you have to have certain assumptions about the world. You have to make assumptions about the slope of the demand and supply curve, so how demand and supply react compared to price. These assumptions are essentially the sensible ones, that a consumer is willing to buy more of something if it's cheaper. Now, there are, of course, some luxury goods where that's not true. Maybe with sports cars, you wouldn't buy more sports cars if they were cheaper because you're a billionaire and you love to buy the most expensive car. But for most goods, that's a reasonable assumption. So you have to make all these assumptions about the world and encodings about what your hypotheses are. But they boil down to combinations, logical combinations of algebraic constraints. And so it's possible, and indeed in a paper we do, to encode that as a real quantifier elimination problem. And it's a very trivial one. It takes only a microsecond for any RQE package to determine that is true. The statement from 1895 is a true one, and indeed, as you would hope, it's over 100 years old, and everyone accepts it. So let's consider a more interesting example. At this, I have to give you a little bit of context. So I was working in partnership with an economist called Casey Mulligan, and he works at the University of Chicago, which is known to be quite a right-wing economics department. Right-wing in the sense that they look at economics theories that encourage lower taxes. And I don't, by the way, I don't subscribe to any political view publicly here or privately, but I'll explain why I was attracted to work with Mulligan in a moment. But Mulligan was in a public debate in the newspaper with Paul Krugman, who's a Nobel Prize winning economist who is probably on the more left-wing side of economics. So he generally thinks that taxes don't have quite such a bad effect on the economy as the right-wing economists would. So they were engaged in this debate over the causes of the last recession, and they were writing articles, kind of critiquing each other's analysis. So in one example, Paul Krugman made a statement, a quite complicated set of assumptions and hypotheses about the cause of the effect of taxes that they were having on the labor market, essentially making the claim that the taxes were causing more unemployment at the moment, and they were debating this fact. So he made this claim in the article, and what Casey Mulligan did then was to write down all of the mathematics in Paul Krugman's article for both the assumptions and the hypotheses, and to put it through one of these real quantifier elimination systems. So again, I'm not going to go through all the details here, it's needlessly technical, but the point was they could all be encoded in our language of polynomials, involving 12 variables, so quite a big one, but with some smart optimizations, problem that could be tackled. And he showed that the theorem was not universally true. That is to say, it wasn't true for all possible real numbers, values of the variables. So it didn't satisfy universal quantification. And then exploring this in the paper, we saw that if you added in 2 additional assumptions, you could make Paul Krugman's argument true. So the additional assumption was basically saying that you had to assume that the supply of labor was more sensitive to wage price than the demand for labor. Now, is that true? Is that a true fact? Well, it depends on the economy. It depends on the moment in history. Sometimes it's true and sometimes it's not. But the point is, it's a fact that you can go and get data for and try and test. And so I said before, I don't subscribe to any particular economic view. I'm not an economist, and I try not to get too political. But the point is that if you are going to argue these economic arguments, you should at least be arguing logically. So you should be making assumptions and hypotheses that are compatible with each other. And then the argument really boils down to the assumptions. So your argument should be, are these assumptions about the world true or not? And you can test each assumption one by one and try and ascertain whether they're true or not. But you shouldn't be arguing about whether these logical assumptions lead to these logical conclusions, because that's just logic, and that's not something we should argue over. Logic is fact. And so I was attracted to work with Casey Mulligan, not because of his political stance, but because he was prepared to subject all of his work to this type of logical analysis to prove that his assumptions did indeed lead to the hypotheses of which he claimed. So we've got some nice papers with him studying a variety of economics problems. So I've now got 10 minutes left. If anyone had any questions now, I'm happy to take them. Or if you like, I can try and talk about some of those algorithmic developments just at a very high level from my last 10 minutes. Okay, so we've tried lots and lots of different things. I don't have time to discuss them all, but I do want to mention just 2 different approaches that we've found really useful. And I want to mention them because I think that they could be useful for lots of other areas of mathematics and computer science as well. So I kind of picked them for their potential reach. So even if you're not interested in quantifier elimination after all of this, still these ideas might be useful for you. So the first one is about taking inspiration from SMT. So I'll define what SMT is and what it means to take inspiration from it. So in this section, I'm looking at a simplified version of quantifier elimination where I only can care about existential quantifiers and all the variables. But that's just a simplifying assumption. Actually, a lot of what I say can be generalized away from that to more general quantification. But the reason this is a nice assumption to make is because now we enter the realm of what is called in computer science satisfiability. So when you're studying a problem that's fully existentially quantified, you're simply saying, can I satisfy? Is there any value of these variables that can satisfy this? And this is an exciting area to look at, because satisfiability, maybe I just skip to this slide here. Satisfiability is probably one of the biggest computer science success stories, aside from perhaps machine learning, so of the last 2 decades. So machine learning and satisfiability, I say, are the 2 runaway success stories in computer science. So satisfiability, that is to say, the study of the Boolean SAT problem, where we just have Boolean logic, has been basically solved, quite frankly. And it's so weird because the SAT problem is, of course, the first NP complete problem. It's meant to be a really, really difficult problem. But what you have here on this slide is the performance of the leading SAT solver, running up only to 2015. It's even better now. And you can see that it's able to study Boolean SAT problems with well over 1,000 clauses in, and indeed tens of thousands of variables. These are incredibly powerful tools that don't seem to be constrained by the NP completeness proof that there exists for the problem. So what's going on here? Well, what's going on here is that the problem is NP-completes and is indeed hard to tackle in the worst case. But what has been observed in practice is that what is the worst case very rarely seems to crop up in the actual examples you apply SAT solvers to. So somehow that traditional big O worst case reasoning that we all learn in our computer science degrees is not really illustrative of the real world, at least not when it comes to SAT solving. And what is SMT solving? Well, SMT solving is simply the use of SAT solving in combination with other technologies. The idea is if you have some logical problem, but it's not Boolean logic, it's say algebraic logic, like I look at, then the idea is to take the logical skeleton of the structure and have it be studied by a SAT solver. And then if the SAT solver says, no, this logic is impossible, then it doesn't matter what the atoms are, it doesn't matter what the polynomial constraints are, it's impossible. But if it is possible, then the SAT solver will suggest to you possible solutions, and you then have to use some other piece of software to see if that solution is valid for the particular theory you're in. So in my case, using something like CAD to see if that combination of polynomial constraints is indeed possible. And if it's not possible, you can rule out, you can certainly rule out that possible solution. You can actually often rule out whole branches of solutions, and so guide the SAT search efficiently through its search space. So that's that's a high level idea, SMT, and I've been working on adapting CAD so that it can be used in this context where it's joint with the SMT solver. So I'll skip all the technical details, but I will just say that we adapted the CAD so that it was inspired, not just hooking it up with a SAT solver, a bit of software engineering hooking two things up, but actually adapting the CAD code so that it was inspired by the same idea of making a guess, seeing if the guess works. And okay, usually the guess doesn't work, but it doesn't work for a reason. You can rule out whole branches of the search space with that region, and we've adapted the theory of CAD to take that search-based approach, if you like, rather than the traditional full decomposition approach. And I'll skip to the punchline. The punchline is that it works really well. And indeed, it's now been used as the algorithm for nonlinear real polynomials in CVC5. And CVC5 is probably the most popular open source SMT solver on the market. It's used widely in academia, but it's also used in industry. For example, Amazon heavily use this and indeed fund a lot of the research groups in this area. And it won the 2022 SMT competition. And most of interest, it won the nonlinear polynomial track of the system using an implementation of our algorithm. So we're very proud to see that. Okay, and in my last couple of minutes, I'll talk about my work with AI, machine learning. So machine learning, I'm sure everyone's very familiar with this. It's hard to escape it these days. The idea is to use big data and statistics to have our software learn to do something that we haven't programmed it to do. So something you might naturally ask is, could I replace all of this mathematics, all of this symbolic computation with machine learning? It's a fair question, and there is a growing body of research on that question. And so in some cases, it's pretty good, especially, differential equation solving, one of the most difficult areas of all mathematics. Neural networks are getting, pretty good at this. I mean, they're not perfect yet, but they're making good progress. But differential equation solving is quite a special mathematical problem because it's kind of a one-way function. It's really hard to solve differential equations, but once you've got a solution, it's very easy to see if the solution's correct. You just substitute it back in. So there's kind of no danger from using AI there, whereas with a lot of other mathematics, just because you've got an answer, it's really not easy to check that if the answer is correct. So we're not NP, we're often in purely exponential space. And so that's a little bit dangerous, I would say. However, nevertheless, in mathematics, often the algorithms that we produce to solve mathematical problems have within them configurations, parameters, hyperparameters, choices that need to be made, and often we don't make them in any particular smart way. We maybe just make them randomly, or we make them using some crude heuristic, and yet these can have a great impact on the efficiency of the code. And my hypothesis is that here machine learning can be used to safely guide mathematics. And indeed, this CAD, quantifier elimination case study, has such a choice, and you may have spotted it earlier. It's the choice of variable ordering. So we need to pick an order in which to study our variables when we build these decompositions. Here we have the same polynomial, but if I project it onto the horizontal axis, I only have 3 cells, the black line, the orange, and the green. But if I project it onto the y-axis, i.e. I look at the y variable first instead of the x variable, I have way more cells. So this choice is somehow doesn't change whether my answer is correct or not, but it does change how much work I have to do to get the answer and how the answer is presented. So I end up with a way load more cells. They're still cylindrical cells that are sign invariant. So if I take one sample point from each and numerically sample, I'm still guaranteed to get a right answer. But the point is, some of those cells could be merged quite safely. It's just that you don't know you can do that if you use the wrong variable ordering. So we tried to study this with machine learning. And the first thing I would say is that it's interesting machine learning, by which I mean it's difficult machine learning. So why is it difficult? Well, first of all, there's no kind of limit on the input space, so it's really hard to come up with a good representation for the neural network. Secondly, supervised learning is hard because you have to label a data set, and labeling a data set means running lots of symbolic computation, which, as we've already established, is really expensive. But unsupervised learning is hard too, because if you just run something once and you get an answer, unless you have anything to compare it against, then you have no real idea as to whether that answer is a good answer or a bad answer. And then there are also really hard questions about what constitutes a representative and meaningful data set. So these are really tricky questions, and that's why I have several PhD students trying to think about them. One thing I would finish my talk with, though, is the idea that as well as speeding up our algorithms, AI could actually perhaps be used to give mathematicians new ideas. So I was inspired by this paper from 2020 by Pfeiffer, Stillman, and Halpern Leinster, and they trained a machine learning model, reinforcement learning agent, actually, to make some choices in a mathematical algorithm. And then they tried to interrogate the model. That was to say, experiment with it, and they come up with some descriptions of how they thought that model was making its choices. But of course, they weren't sure because it's a black box. These were empirical observations. But those empirical observations led to new mathematical theorems. So it kind of inspired new mathematics. So the question is, can we automate that process somehow? And so we have a paper that was just accepted this week, looking at the use of explainable AI to produce information to guide non-AI based reasoning. And so again, we looked at this cylindrical algebraic decomposition problem and the variable ordering, and the features that the SHAP AI tool used to identified as the most impactful of all the tons of features we were making use of. We then took those and used it to make a simple if statement, human level heuristic, which dramatically outperformed the existing ones for the problem. So it kind of demonstrates the potential of explainable AI as an exploratory tool for subsequent human optimization of algorithms if we don't want to fully hand over the keys to the AI in the future. So that's the end of my talk. I'm only 4 minutes late. So I do thank you for hanging around and listening. I hope it was interesting. And that's all I have. Thank you.